Welcome to the very first lecture on this course, Digital Logic and Systems. So, what we see is that essentially there are three words which make up the name of this course, that is Digital Logic Systems. So let's try to understand what each of these words actually are trying to convey. So the first word, digital, is trying to convey something to do with digits. We are all familiar with digits. For example, 0, 1, 2, and so on. They are digits with which numbers are made up. Logic. Logic is what? Logic is something which we associate with our own brain and thinking. When we say that this person is a very logical person, that means that this person thinks in a certain well-defined manner and takes the decisions in a very well thought out manner. That is what is called as logical. So therefore, logic essentially refers to the way with which we think and make decisions. This is what is logic, the way in which we think and make decisions. What about systems? System in its basic sense in the electronic context refers to an interconnection of well-known blocks or familiar blocks to achieve a certain purpose. For example, an amplifier is a system. It consists of multiple known elements, for example, transistors, resistors, and so on. And they are connected in a particular manner to achieve something, that is amplification. Now, all these words that we just discussed, we are going to look at them in an electrical sense or an electronic sense. We are going to try to design systems which are electronic, and we are going to try and take a look at the means needed to use these things called digits as well as logic to arrive at certain systems to accomplish certain tasks. Now, to do this, we need to essentially first correlate what these words essentially are implying, how they are interdependent on each other. Right. So let's look at this word called logic. We said that logic essentially refers to the way in which we think and make decisions. So therefore, what seems to be the mathematical representation of logic is that the output of our logic has to be some kind of a decision. The output of our logic has to be some kind of decision. So therefore, let us say the logic output is essentially a decision. Let's call this decision as some variable y. Traditionally, y has been associated as a letter for denoting outputs of any system. Let's suppose we say that y is my logic decision. And how do I arrive at this decision? If I am a logical person, I will arrive at this decision based on the information that we have, and those information must satisfy some conditions, let's say. So therefore I will say y is some kind of a function of the information we have, right? So this is a very broad definition. Information that we have could be anything. So here is where the word digital essentially comes in. Can we represent our decisions and this information that we have by means of digits? Well, we certainly can. We certainly can. Let us try to see a real life scenario under which we could look at logic both as a way in which we think and make decisions using the information that we have. Also, we will look at this using digits. Now, let's take a very simple example where there's a child. There's a child who wants his parents to buy him a video game. Who wants his parents to buy him a video game. Now, obviously, the parents have to take this decision in a very well thought out and a logical manner. So therefore, they set some conditions for the child. And in other words, they give the child some information, or the information that the parents themselves will have. So let's say that the decision, which is y in this case, would be defined as whether the child should be given the video game. Now, if this decision is denoted as y, there could only be two possible outcomes. Yes or no. Either the child gets the video game or he does not get the video game. There are no two ways. There is no other way. So it's either yes or no. It's either yes or no. So therefore, for the parents to take this decision, to arrive at a definite outcome of either yes or no, certain information must be known. Certain constraints must be met. So therefore, the information to help the parents to arrive at their decision. Now there could be one piece of information There could be 2 pieces of information. There could be 3 pieces of information. So on and so forth. In most situations in life, whether it is digital logic or not, you will appreciate that taking most of the important decisions in life involves more than one piece of information. So therefore, let us say that there are 2 pieces of information, A and B. So let's say this A is whether the child does well in school. Whether he's been a good student, whether he is achieved a certain good result. And the second piece of information B is whether the child has done some other activity. For example, when parents set constraints for their children, they usually keep it with some kind of a home task. So let's say, for example, whether the child has cleaned his room every day. So now the parents say that we will give the child the video game that he wants if and only if both of these tasks are done. That is, if the child has done well in school, as well as the child should be cleaning his room every day. So therefore, satisfying these pieces of information, there could only be 2 possible outcomes, yes or no. That is, either the child does well in school or does not do well in school, and whether the child has cleaned his room every day or not. These are the things with which we can proceed. So therefore, let us now denote the parent's logic in the form of a sentence. That is, the child So this is what the parents say. So if we try to denote the logic and what are the possible outcomes depending on what are the pieces of information that is available, we can note them down in a tabular format. We can note it down in a tabular format. That is, let's say we say A and B are the 2 pieces of information and Y is the decision output. Now, suppose A is not satisfied and B is also not satisfied. So the child neither does well in school nor does he clean his room. So therefore, there is no question of giving him the bike. Now suppose the child does not do well in school, but he is able to clean his room every day. Then what happens? Well, the condition is very clear. The parents have said that the child gets the video game if he does well in school and he cleans his room every day. So clearly, they want both tasks to be satisfied. So therefore, the child will not get the video game in this case. Conversely, if the child does well in school, but unfortunately does not clean his room every day, As per the condition, no matter how well he does in school, he will not get what he wants. The only time he will get what he wants is when both conditions are satisfied, and then the outcome will be yes. So now what we are seeing in this kind of a logic, both conditions need to be satisfied. So this is called as AND logic. Reason is very simple, because of the word AND over here. Because of the word AND. Which means that it is quite clear that the parents want both the conditions to be satisfied in order for the child to get what he wants. So this is an example of parents being very strict. Now, conversely, there are other kinds of logic also. If the parents are slightly a bit more lenient, so to speak, and they say that essentially the child will get the video game if he either does well in school or he cleans his room every day. So that is a bit more relaxed condition. So that is called OR logic. Now the point is that whatever be the logic, which we shall see in more detail shortly in the course, what we are seeing is that when we are tabulating the decision making process in this way, both inputs and outputs can be valued as in the form of yeses and nos. So if I can say that if I want to now introduce digits, I can say a no corresponds to a 0 and a yes corresponds to a 1. Similar at the output, a no corresponds to a 0 and a yes corresponds to a 1. I can just assign a number to it. If you want, you can also call no as a 1 and yes as a 0. It's perfectly alright. Nothing stops you. The point is that we can associate our decision making process with some kind of a number. And here is where the concept of digit comes in. Here is where the concept of digit comes in. We can associate our decision making process with some numbers. So, having said that, let us now try to understand that in the electronic sense, what does digital mean? So to understand digital, we must ask ourselves before that, what is the opposite of digital? The opposite of digital is something called as analog. Now, analog system is something where the electrical quantities are construed as continuous functions of time. So electrical quantities are represented as continuous functions of time. Now, for instance, when I say electrical quantity, it could mean voltage, current, so on and so forth. There could be some non-electrical quantity which could be represented also as a function of time. a continuous function of time, and that's perfectly acceptable. For example, what is one of the easiest examples or instances of analog systems that we come across in our daily life? Say, for example, when we look at the voltage that comes to the plug points in our homes. So therefore, we know that it's a sine wave that looks something like this, whose amplitude is roughly about 230 volts. Its frequency is 50 hertz. But the point is that at each and every possible instant in time, this has a very well-defined value. Defined for all possible values of time t. This is voltage. For instance, there could also be random functions or quantities which change a little randomly. Say, for example, I am designing a system which has to read the temperature in some kind of a environment. For example, there are industrial ovens and furnaces, but the temperature has to be monitored all the time. Or in a more general or more familiar application, let's say you are monitoring the temperature just outside your house and you would like to know what the temperature is or how it changes as a function of time. You could very easily connect a temperature sensor and it will give you an output as a function of time. So let us say if the temperature looks something like this, temperature is a function of time, what we can say is that, let's say it's a winter's day somewhere in India. So let's say at 5 in the morning, or let's say at 6 in the morning, we measure the temperature. It's close to 15 degrees Celsius. And then it continues to sort of increase as the sun comes out. And let's say by the time it is 12 o'clock, 12 noon, the temperature comes to somewhere about, say, let's say 27 degrees Celsius. And by the time it's evening, 6 o'clock, the temperature comes to somewhere about, let's say, minus 20 degrees. No, sorry, not minus, plus 20 degrees. Minus would be too cold. So this is 20 degrees C. And the temperature, let's say it keeps decreasing after that. So what we are seeing is that the temperature profile of that place as a function of time is a continuous function. Sometimes it may also be very irregular depending on what the place is. So these are some examples where we have electrical quantities that are continuous functions of time. And suppose we would like to measure them. The voltage can be very easily measured with voltage sensors or multimeters, whereas the temperature sensors are also very widely available, and these are ideal for analog systems. So therefore, now we need to ask ourselves, the voltage is analog, the temperature is analog, that means they are continuously defined. For example, between 6 o'clock to 12 o'clock, there are infinite number of time points. So that is like saying this temperature is a continuous function of time. So we must ask ourselves, if these quantities are continuous functions of time and are well suited for analog systems, then in that case, why should we bother about digital? Why not just go ahead and design them the way they are? That is, design them as analog systems themselves. That's a very good question. That's a very good question. So therefore, we have to ask ourselves, what are the drawbacks of analog systems? Is there some drawback in an analog system which is very important and therefore we need to go for digital? Well, first and foremost, what we notice is that for, let us say, the sensor to read this voltage, it must be always on, because the voltage exists at each and every instant of time. So the sensor has to read this data all the time. So therefore, if I want to write the drawbacks of analog, the first drawback is that the system is always on. So what is the problem with that? The problem is that if the system is always on, there will be a lot of power consumption or a lot of power dissipation. Well, there are cases in digital systems also where the system is always on, but the power can be significantly reduced. Second, most importantly, the problem comes in storage. If I want to take this value and store it somewhere, take some value of some quantity at some instant of time and store it somewhere, that storage facility is extremely limited, because analog systems essentially have to deal with quantities which have values at each and every possible instant of time. So that's like saying, if I have an analog quantity, how many time instants data I can collect? If I, let us say, want to know the data of the voltage as a function of time for various time instants, then that task becomes extremely difficult, because I have to now try to get the data at each and every possible instant of time, which is just not possible. Between any 2 points on this graph, there exists an infinite number of points. So therefore, storage of analog systems or analog quantities becomes extremely difficult. Because the number of data points essentially tends to infinity. So, third, the third drawback of analog systems is that they are very prone to noise. They are very prone to noise. Now, what is noise? Noise is any quantity that is undesired, any additional quantity which may superimpose itself on the quantity that we are interested in, and it might falsify the information. Let us say that we have this nice temperature profile and somehow we see that there's a fluctuation over here. Some noise has come. Now, the sources of noise are many. Without getting into those details or without bothering about where the noise comes from. Let us say there is some noise over here. Now the sensor will not know that. It will just think that, okay, the temperature will increase like this, decrease like this, and then come back to its old trajectory. So therefore, in analog systems, often it becomes very difficult to distinguish the signal, the actual signal, from the noise. Sometimes, right? So these are some of the drawbacks. Because of this, it was felt worthwhile many years back to investigate what is meant by digital systems. So now, the first thing that people asked was, how do we convert something analog into something digital? Now, what does that mean? Let us look at the storage point of view. We know that any analog quantity, the storage is impossible because number of data points between any 2 points we desired is infinite. So the first thing that we need to do is to convert this continuous function into some form of a discontinuous function. So therefore, let us look at conversion from analog into digital. So what we need to do? We need to first convert a continuous quantity into a discontinuous quantity. We need to convert a continuous quantity into a discontinuous quantity. When I say discontinuous, I mean as a function of time. Because we need finite number of time points to store that data. So let us say we have a very simple voltage function, a voltage waveform as a function of time. Looks like this, let us say. And what we will do, we will essentially convert this continuous function into this discontinuous quantity as a function of time, which is also called a discrete quantity. Which is also called as a discrete quantity. And we will do so by taking pictures of this signal at certain points of time. When I say picture, I don't mean literally using a camera, but to observe its values at regular intervals of time. So let us say I take the photo at time t equal to 0. I can take another picture at some instant of time which is above 0. So the best way to go about this is to take these pictures at regular intervals of time. So let us say this is 0. Since I am taking snapshots of the signal, or pictures, I will call this time as Ts. So since I would like to do this at regular intervals of time, I can do this at 2Ts, I can do this at 3Ts, I can do this at 4Ts, 5Ts, and so on. So in this case, I will observe that the values are quite different. And so on. So what I am essentially doing is that I am taking snapshots of the signal to observe different values at different points of time. So it's like saying I am not observing the whole signal, but rather looking at it at different points of time, or rather what we call as we are sampling the signal. This process is called as sampling. Let me explain this with a bit of an easier real life example. Let us say you would like to go to a sweet shop to buy some sweets for your family function. Now let us say you need to place a big order of sweets. Now when you go to the sweet shop, the confectioner will show you the different kinds of sweets that they have. Now it will not be possible for you to check out each and every possible sweet unless you tell the confectioner that, okay, I'll be placing a big order of sweets from your shop. So before that, I would like to know how the sweets are. So please give me one sweet from each variety, right? So that process is actually called as sampling, and many shops indeed do that. So what you will do is that you will just have one sweet from that lot and you will taste it and see whether it is indeed good enough or not. That is called as sampling. Now, the question is, how many such samples should be taken? Well, the more the better, right? Because the more samples you take, the more snapshots you take, the more pictures of the signal you take, the closer it will be to its actual analog continuous form. But then again, if the number of sampling points increase, the storage might again become a problem. So therefore, we would like to take many samples, but at the same time, we would like to ensure that our storage requirements are met. So the converse of this statement is that if we are taking less number of samples, we must ensure that if we are taking less number of samples, we must take it in such a way that we do not miss any important part of the signal. Suppose I take a sample here, here, and here. Is that sufficient? Not at all. Because if I just observe these three samples, they're all zero. So it would appear to me as if the signal is always zero. On the other hand, if I take good number of samples, let's say the way I've done over here, the sample signal will look like this. So if I observe these samples over a period of time, I can say that yes, it is indeed a sine wave. But if I reduce my number of samples, I will lose complete knowledge of the actual nature of the signal, and that is disastrous. So therefore, there exists something called as a sampling theorem, which was essentially a mathematical relation derived by some scientists who said that the rate of sampling should be high, or something that we call as the sampling frequency. The sampling frequency Fs, which is nothing but 1 by Ts. This sampling should be done at such an interval such that you do not miss even those signals which are of high frequency, or those components which are of very high frequency. Now, I will not get into the details of the sampling theorem. I will just let you know that the sampling theorem was proposed by a group of mathematicians whose names were Nyquist, Shannon, and Whittaker. Who said that the sampling frequency should be above a certain value. Now, what that value is not of very much importance from this course perspective. So, if we want to correlate this with our discussion about the sweets, the question is that if you have decided what variety of sweet that you want to place the order on, how many samples should you taste? Or how many sweets should you have for free, just to gauge the idea that the whole lot of sweets is actually good and are worth placing an order on? Well, if you have only one sample out of the lot, it may so happen that the rest of the sweets, many of them are bad, or they don't taste well, or the shopkeeper could also play foul and replace sweets in the box with poor quality sweets. So therefore, you need to ensure that you are sampling properly. So therefore, you need to ensure that you take enough number of samples. The bottom line is that to convert from analog into digital, you need to take snapshots of the signal at certain instances of time, which are also called as samples. So number of samples should ideally be as high as possible. So that the nature of the signal is preserved. So what we see is that once we take the sample, let us say for the first sample the value we see is 0. For each sample you will get some kind of a voltage value. Let us say this one is 2 volts, this one is 3 volts, this one is 5 volts. I'm just giving an example. This is 7 volts, this is 6 volts, this is 4 volts, and so on. Each sample could have its own value. Each sample will have its own value. So therefore, with this what we are seeing is that the notion of digital is again coming back. Each sample has a value. Now we have to see whether we can represent these values using digits but in a more uniform manner. And what that is, we shall discuss in the next lecture. So in this particular class, we started with the discussion of what is the meaning of the word digital, what is the meaning of the word logic, and what is system. We saw what is an example of logic in real life, and we saw that from an electronic perspective, what is meant by digital, or rather we started the discussion on that, starting with what is conventional or existing, that is analog systems, and how you can convert an analog signal into a discrete signal. We also discussed some of the basic drawbacks of analog signals which motivate us to look at digital signals also. We shall continue from this very same point in the next lecture. Thank you.